Well, good morning, everyone, and welcome to this congressional briefing on hydraulic fracturing, the state of the science. Thanks to Representative Jerry Connolly for being our host today. This series is organized by the U.S. Geological Survey to increase awareness of their role and to support the role of science in decision-making. Also hosting today is the American Geophysical Union. My name is Harvey Thorleifson. I will be your moderator today. I am the State Geologist of Minnesota and President-elect of the Association of American State Geologists. Hydraulic fracturing is playing a key role in making unconventional oil and gas resources economically viable and adding to our domestic energy production. There are many benefits to producing these oil and gas resources, but there are also concerns about possible environmental effects associated with development. In collaboration with partners, the USGS conducts research that is directly applicable to understanding unconventional oil and gas resources and possible impacts related to energy production and disposal of produced waters. The USGS remains neutral regarding specific actions or procedures and rather provides decision makers with unbiased scientific information for planning, for developing policy, and for making resource management decisions. The overall USGS goal is to provide timely, relevant science on research topics that can support sound policy decisions made by the local, state, and federal agencies that are responsible for ensuring the prudent development of energy resources while protecting human and environmental health. Today we have three speakers who will discuss both opportunities and challenges that come along with hydraulic fracturing. We have scheduled time after their presentations for your questions and discussion, so please hold your questions until the end. Our first speaker is Brenda Pierce, Program Coordinator for the USGS Energy Resources Program. Brenda manages and oversees the Energy Resources Program, including research and assessments on all geologically based energy resources and the environmental and human health effects of energy occurrence and use. Brenda.
Thank you, Harvey, and thank you all for coming. We know it's a topic of great interest, and we appreciate your time to hear about how we help in providing science for hydraulic fracturing and, of course, for much more as well. So before we jump into hydraulic fracturing, you'll have to bear with me. I'm a geologist, and so I have to give you a very short tutorial on geology and actually what these resources are. So I appreciate your patience. The way that the U.S. Geological Survey looks at oil and gas resources is from what's called a total petroleum system. And if you look at this, here's the surface of the earth with some cartoon drill rigs into what we call conventional oil and gas accumulations. This would then be the unconventional, the shale gas, the tight oil. How does oil and gas form? Very simply, and do bear with me, you have to have sometime in the geologic past enough organic material that has actually accumulated, that is rich enough and thick enough to actually form the basis for oil and gas. You then have to have it buried under lots of other sediments, and buried so that it reaches a temperature range that the organic material can actually form oil, and if it's heated higher, it can form gas. If it's heated too much, you won't have either, and if it's not heated to a minimum temperature, you will have neither. So you need a very specific set of geologic conditions, and the timing has to be right to actually form oil and gas. In conventional resources, which the United States has developed for more than 100 years, the oil and gas that's generated at depth in the source rock, this is what the organic material becomes, then migrates up through the system through fractures and fissures because oil and gas is naturally buoyant. Often it will go to the surface naturally. There are seeps in the Gulf of Mexico, on the North Slope of Alaska, but often it becomes entrapped in traps. What you need for that is a rock that has actually pore space within that rock to house the oil and gas, and I have some pictures of this in a minute. You also need an impermeable seal on top of those traps so that the oil and gas cannot go further up toward the surface. So these are conventional oil and gas accumulations, and this is what we've been developing for a long time. And simplistically, but in a nutshell, the difference between conventional oil and gas resources and these unconventional oil and gas resources is that the unconventional has stayed in the source rock, or is very close to it. It has not migrated up through the system. It is held so tightly in that rock that you have to actually artificially fracture it or add some technology to it, and that's why one has to hydrofracture these. Because it is the oil and gas, same type of oil and gas, but it is held in this rock formation rather than having migrated up through the system. And because these are much larger systems across the landscape, the U.S. Geological Survey calls these continuous resources. Doesn't mean that every molecule is found in every bit of rock, but they're much more continuous across the landscape instead of discrete accumulations found like are in conventional, that are usually water-bounded and are more easily found on seismic lines, those kinds of things, and are actually more easily developed. Not easy, but more easily than these continuous. And so when we say continuous accumulations, we mean shale gas, shale oil, not oil shale oil, tight gas, coal bed methane, those types. So that's your geology lesson for the day. And again, that's why we need to artificially stimulate, add technology to these continuous resources in order to get them. So here is a little bit more geology. So this is a conventional reservoir. This is a hand specimen, what you might see if you picked up a rock. And this is it in a thin section. This blue is the pore space in the rock that's been dyed so one can see it. You can see that the pore space is interconnected, and the blue is where the oil and gas resides in a conventional reservoir. Often you don't need to do anything except depressurize the reservoir to get the oil and gas to flow because these pore spaces are interconnected. Compare this, though, to a continuous reservoir. This is about the same scale. The pore spaces are much tighter and not connected at all. Again, this is the hand specimen, and this is the photomicrograph of what you'd see under the microscope. You have to artificially connect this pore space to get the oil and gas to flow to the wellbore and then up to the surface. And again, in a nutshell, that's the basic difference between conventional and continuous resources. So one more slide on this and we'll move on. These are basically the same scale, but this is a conventional reservoir, again, with the blue dyed pore space that you can see the interconnectedness. And this is a continuous one that actually has quartz, mineral overgrowths on those pore spaces. So sometimes you actually have secondary closing of pore spaces, or there was very little pore space to begin with. And this is what you have to hydraulically fracture to get that interconnected pore space to get the oil and gas to flow. So why is all that important? Because you develop conventional resources very differently than continuous resources. The geology is different. Our understanding of them is different. They occur in different areas. And so the geology is pretty important. So what the U.S. Geological Survey does is assess these resources of what is the, and this is important, undiscovered, technically recoverable resources. There's a lot of confusion about resource assessments out there because they all look at different parts of the spectrum of the resource pie. What we do is the undiscovered resources. So it's not reserves, it's not what's currently being produced, it's that unknown, that undiscovered part of that resource spectrum, but what is technically recoverable with today's technology and industry practice. So we don't incorporate economics in these except that it is technically recoverable. And we go to some great pains to look at what is technically recoverable, and I have a couple slides on that just to show you that. An assessment is an estimate of the measurement uncertainty, and so what that means is that you'll see a lot of one numbers floating around about resource assessments, but what the USGS does is give a probability distribution because there is great uncertainty in these. Even with reserves, they change over time, but undiscovered resources definitely change over time because they are undiscovered. So we give a probability distribution of a minimum, a maximum, and a mean. And that wideness of the distribution shows how much we're assured of those numbers or unassured. And every time we get more information, we can refine these resource estimates so that they're better. So these continuous methodology, and I won't spend a lot of time on this, but it is different than a conventional methodology. All of our assessment methodology, or all of our assessments are geologically based, and that's critical because, as I mentioned, geology is very critical to these resources and developing them and understanding them, and then actually producing them. And so we do a very detailed geologic study of each of these basins that we look at and each of the assessment units within the basin that we look at. We actually look at the drainage areas of the well. So look at this. This is a surface view of the earth, acre spacings, and this is actually real data from the Woodford Shale. And you look at how variable these are wells. Some squares have no wells in them, and some have up to 8. So they're quite variable. These are very different than conventional resources. So we look at the drainage areas of the wells. We look at the number of potential cells that each one of these can have, and we really look at engineering data. We work with industry not to do the assessment, but to understand what is technically recoverable in each type of these, because each one is different. You can't necessarily compare the Woodford to the Bakken to the Marcellus. Geologically, they're all very different, and each is developed somewhat differently. So we take great pains to look at how each of these is being developed, and so we can actually apply that to the undiscovered portion. So we very carefully look at the engineering data, the well production data, and put that with our geology, and then the estimated ultimate recovery of each of these wells. And so the upshot is that we take those data, feed it through some statistical analyses, and that's how we come up with a quantitative estimate, but with the probabilities. And this is just one product that we have. These are our bubble maps for both continuous oil and continuous gas throughout the United States. And the size of the bubble is in relationship to the size of the whole resource within that area, not the probability distribution. And so this is just, again, one product that you can see a quick view of the distribution throughout the United States. We have much more detailed information that also focuses on this kind of information and detailed information per basin. And then we also break it down to shale gas versus tight gas because they are different. They're developed in different proportions. They're developed somewhat differently, and they do make a difference. And so it's important to understand them. We assess them with the same assessment methodology, so they're comparable, but we do break them out because they're geologically different. We break them out in the results. And we just recently started expanding looking at these continuous type resources into frontier areas. We just recently released an estimate of the source rocks or the continuous type resources on the Alaska North Slope. Never had to do this before, and nobody has ever done this before. But as we know from the lower 48, these types of resources are now economically viable in certain settings. And so it was important to us to start looking at this in frontier areas like our own areas of the Alaska North Slope, as well as globally, and we're embarking on that as well. So our estimates, I told you, we do a different probability distribution, so range from 0 to 2 billion barrels of oil, and from 0 to nearly 80 trillion cubic feet of natural gas on the Alaska North Slope. So some oil, certainly a lot of gas. Gas is currently a stranded resource on the Alaska North Slope, but I think it's important to understand our domestic resources so policy and decision makers know what may be potential out there for future use. And it's important to point out that resource assessments change over time. I think everybody knows this, but of course the Bakken is our best example. We assessed the Bakken in 1995, the last time we had assessed it, and we came out with a mean total of 150 million barrels of oil that was technically recoverable at the time. We reassessed the Bakken a few years ago and released it in 2008, and we came out with a mean estimate of 3.65 billion barrels of technically recoverable. I don't think we actually got it wrong in 95 because by a few years ago, only 100 million barrels had been produced. What really changed was the technology. Significant technological advances in what was done in the Barnett Shale and some other gases, the horizontal drilling and the hydrofracturing, that technology was taken to the Bakken, and because it's oil and the price of oil, just phenomenally 20-fold increase in what was technically recoverable, still undiscovered. So that's in addition to what has been produced and is being produced. So significant changes can happen. Sometimes estimates actually go down. That happens too. If companies dry drill holes, we take that into consideration. Anytime you get new information and data, often they don't change this significantly, but sometimes they do. So improved geologic understanding is a key factor as well, but technological developments especially can change what's technically recoverable, and that makes intuitive sense. So that's why the USGS continuously reassesses things, so that we can have a current estimate of what is out there, what's technically recoverable, what can we add to our portfolio of resources, and possibly make them reserves. To put this into perspective, the next slide is a slide of the development of the Bakken. So it's going to show you through time. So up in the upper right-hand corner will be the date, and it will show you the development of the Bakken, and it will show you, much like our assessment, that at first it was pretty slow. But then you hit a few years ago, and it's just huge, quickly. So watch the development and watch the year, and it's a pretty phenomenal development. I mean, it just exponentially takes off. So, I mean, this is production, the year. You will see a few key discoveries have really then prompted discovery across the whole field, new applications of technology. This may or may not happen everywhere. I mean, a lot of people have high hopes for all of these types of resources, but again, they're all different. Some of the gas plays can't make it because of the gas price. So it's important to keep this in perspective that this is phenomenal, but this may or may not be able to be transferable everywhere. So again, we look at this and why is it important to do a resource estimate? Well, that's partly the reason. Partly the reason is that not too long ago, 20, 25 years ago, these resources were not at all anything. I mean, we just didn't think they were going to contribute to the national energy mix. Coal bed methane was the first one that we learned a lot about, and then shale gas has taken off. Tight gas is also a large percentage of the domestic resource, but shale gas recently has been important. So it's important to understand our future potential resource, and USGS plays a key role in that. And that directly relates to hydraulic fracturing, because these continuous resources, as I mentioned earlier, really need hydraulic fracturing to be able to stimulate the production in the oil and gas. And so if you don't know where the future potential resources are, or let me put it positively, if you know where the future potential resources are, how much is that potential, you can geologically characterize them, you can probably get ahead of production and understand some of the things that you need, regulatory or environmentally, et cetera, before actual production happens. So both from an energy mix perspective, from an energy security perspective, from environmental concerns, I just think it's important to really have that basic information of future potential resources. However, we do understand that there are also concerns associated with it, and my colleagues will talk a lot about that. Water use, the chemicals used, the fate of the injected fluid, and the flowback quality. And at the USGS, we are doing quite a bit of water quality work in the Energy Resources Program alone. We're looking at produced waters associated with oil and gas development. We're doing a number of those things. This is the Bakken itself, and you can see the extent of our assessment units that we looked at overlain by hydraulically fractured wells, and you saw how extent they were in that little movie module. But in this area, we're actually now developing a methodology to quantify the amount of water use needed for these unconventional continuous type resources. And so we hope to develop that may be applicable not just to the Bakken, but the other things, because the water energy nexus is the really big question. So we're developing that now. We're looking at across the United States. You can see this interface happening everywhere. This is our produced waters database with shale gas plays alone. Forget the tight gas and the coal bed methane. So these are all issues. We're looking at other sources of water for potential non-potable water uses for hydrofracturing and those kinds of things. So in a nutshell, that's what we're doing. And without hesitation, I will turn it back to Harvey so you can hear from our other speakers. Thank you.
Thank you, Brenda. Our next speaker is Rick Hammack, who works for the DOE National Energy Technology Lab in Pittsburgh. He coordinates multi-agency baseline environmental studies for monitoring unconventional gas development. He has performed mineral assessments of public lands and developed effective treatments for mining and wastewaters for the U.S. Bureau of Mines. Rick?
Thanks, Harvey. I'm always appreciative of a packed house. Specifically today, I'm going to talk about some collaborative projects that we have, the DOE has with the USGS and relating to hydrofracturing. I started working on cooperative projects with the USGS back in 2005 when we were working on management of produced water for coal bed methane mostly in Wyoming. And since then, we've looked at the origin of salts in the water produced from Marcellus wells. But most recently, we have two studies right now that address the public's concern about the safety and the environmental impacts of unconventional gas development, shale gas development, and hydraulic fracturing in particular. And that's what I want to talk about today. The objectives of these two studies is to provide, as it says up there, a comprehensive science-based catalog of the environmental impacts of shale gas development. Now, we've already looked at this some, and we know that we have seen some environmental changes that you might consider to be positive changes. For example, there are certain bird species that their population's been in decline since the 1960s. But in areas where Marcellus shale gas is occurring, some of these populations are increasing in response to it. There are also some work that's been done, again with birds, where they look at the overall population of birds in these Marcellus areas, and they realize that the population has increased and the diversity of the birds. This is Margaret Brittingham's work in Penn State. But the downside of that is that some of the species that are responsible for this increase are undesirable species. So that's it's undecided right now whether that's a positive or negative or just a so-so response. But there are adverse environmental changes that occur with hydraulic fracturing. And part of our job is to find ways to mitigate those, either through different management techniques or the development of new technology. And of course, the bottom line of all this is develop a body of knowledge that regulators can refer to and that results in better informed decisions on their part. Today I'm going to talk about two sites, both in southwestern Pennsylvania. One is better known than the other. The Washington County site, it's better known because there are more agencies working at that site, and it has also been selected to be a prospective case study by the EPA's Hydraulic Fracturing Task Force. So there's quite a bit of a publicity for that site. That site is a baseline monitoring site where, in essence, we're starting with a clean sheet of paper. No development has occurred at this site, so we're there very early so we can document the conditions that exist before any development takes place. And then we can monitor the changes to that baseline as shale gas development goes through its various stages. And we'll talk about that a little more later. The Greene County site, only the USGS and DOE are working at that site, so it's not as well known, but it is a perfect site to look at hydraulic fracturing underground. Pretty much people are suspect of hydraulic fracturing because it's something that takes place underground where they can't see it. It's kind of like a black box. And our whole intent here is to illuminate that black box and show exactly what's going on and inform the public about what's happening. This is the Washington County site. As you can see, there's nothing there. No development has taken place. It was a farm at one time. Now it's being reclaimed by trees. There is absolutely nothing there but thorn bushes and poison ivy. And there's lots of people out there documenting every thorn bush and poison ivy plant and tick and everything else that happens to be there. Now, later this summer, the bulldozers will come here and the drill pad will be built right in that field that you see. And then later on, maybe towards the end of this year or even through the winter, two horizontal Marcellus shale wells will be drilled here. So this is kind of a timeline where we are. We're right here, pre-development. We have 1 year to establish and document baseline conditions at that site. And we're doing comprehensive monitoring here. Everything from A, air quality, to Z, zebra mussels. We're doing everything. Anything you can think of, we're trying to look at this site. And then we're going to continue monitoring those same parameters. Well, we'll document what's there to start with. And then after the site is constructed, we'll look at it again, see what's changed. After the wells have been drilled, we'll look at it again. After hydraulic fracturing, same thing. And then we'll continue that on into production and to see the overall effect. Now, because this site, the monitoring at this site is so comprehensive, no one agency has a skill set to monitor all the parameters that we wanted to monitor. So as you can see here, there are 5 cabinet-level agencies that are working at the site, 6 federal agencies in all, as well as 2 state agencies. And I'd like to have something to report, but because we're in the baseline phase, that's not really too exciting, documenting the conditions in a field, other than the poison ivy I already reported to you. But if you come back in probably another year, we'll know the changes that have taken place due to construction, due to drilling, and probably due to hydraulic fracturing. And then what would be nice is to look at it again in 5 years after the site has been restored to its original condition, and then that's the full circle. I'm going to use this slide to segue into the Greene County site, because it's really an ideal site for looking at subsurface hydraulic fracturing effects. Now, what we have here is had depth plotted along the y-axis here, and we have several things plotted in here. Up here in the blue, we have the depth, the maximum depth to the base of drinking water. Drinking water is determined by the amount of total dissolved solids in it. So there's water down in here. It's just that it's too salty to drink. So this up here, this shows the depth for drinkable water. This is actually a plot that was made by industry, and it was presented to the EPA at least twice that I know of, so they're very much aware of this. But what it also shows is down here in the red, this red line is the depth of the Marcellus Shale in various areas. And on top of that, it shows these jagged lines shown in blue here, light blue, and then dark blue down below. This is the upward extent of the hydraulically induced fractures that are created whenever they fracture this rock. And you can see that the fractures mostly go up, very few of them go downward. But what's not shown here is most of the growth is laterally in and out of the slide here. But the reason industry presented this is they wanted to show how much solid rock is between the groundwater that we wanted to protect up here and the most upward extent of these fractures that are being created down below. And for the most part, that's true, except there are other considerations that need to be taken into account. And one is faults. So faults are when the rock breaks, and that forms a plane, and the plane allows fluids to move up it. It's a crack. The fluids can move up the crack. And if you have a crack like this that goes all the way from the Marcellus clear to the surface into the drinking water, that's a problem, because that provides a quick pathway for fracking fluids down here to migrate up here and contaminate the drinking water. But companies these are pretty easily seen on surface seismic. Companies know where these are. Companies lay out their wells so as to avoid these. However, what is not always seen there are a lot more faults that terminate. They break through the Marcellus, but then they terminate in the upper Devonian here. those wells are a little harder to see on seismic. So that's one what I would call a vulnerability. Another one is existing wells. Pennsylvania, for example, has a longer history of oil and gas production than any other state in the United States. Starting in 1859 with the Drake well, there were many thousands of wells drilled before 1921, and that's when the Pennsylvania passed the first laws that required wells to be plugged and started keeping track of where these wells are. So there are a lot of wells out there. We don't know exactly where they are. Lots of times, these old operators, whenever they drilled the well that was sub-economic, they would pull the casing from the well and take it to the next well and use it in the next well. So what we have out there are a lot of holes in the ground, and they're unplugged. So if your fault happens to communicate to one of these wells, the good thing about most of these old wells is they tend to be shallow. They were drilled to the lower Mississippi and upper Devonian mainly. Still 4,000 feet above the Marcellus. But if you have communication between these faults and those wells, then you can have a problem at the surface. And then the final thing is, much later we have wells that are drilled deeper all the way to the Marcellus, or even through the Marcellus and down to the Oriskany. And these wells have poor cement in some cases. And poor cement allows gas to migrate up the outside of the well, the annulus, all the way up to the surface, where it can spread out into permeable formations in the near surface. But as far as the Greene County site goes, we have all these vulnerabilities there in one place. So we have an opportunity right there to examine and quantify all of these. This is a picture of microseismic. It's one way that we use to measure frac heights. We're doing this right now. We're fracturing right now, and we have microseismic on site. So we're monitoring how high up these fractures go. And this is one I wanted to present here. How microseismic works is, well, whenever you're fracturing rock, you're pumping in fluids. It increases the pressure on that rock and stresses it until it breaks and snaps. That snap creates a sound that can be detected by these geophones that you see here. These geophones are suspended in a vertical well. And that's what these dots are right here, are geophones. And they can tell exactly where that snap occurred. And that's what all these things are here. These are snaps that occurred in response to fluid being injected into the rock formation. Now, as you would expect, you expect a lot of rock to be broken down here where the Marcellus is. This is in the formation. We don't expect a whole lot of rock breakage above the Tully limestone, which is generally thought to be an upper frac barrier for the Marcellus. But in this case, when they were injecting fluid in this particular stage, it communicated with a fault that took it up here. So we're breaking rock, barren rock, up in the upper Devonian. And in this case, we're breaking a considerable volume of rock. This is the Greene County site. It has 3 horizontal Marcellus wells that are being fracked right now as I speak. We have microseismic deployed in this vertical well right here. This vertical well goes down. It's a Marcellus well too, but it's a vertical Marcellus well. So we have geophones in this well, which puts it in the front row position to monitor the hydraulic fracturing, both this lateral and this lateral. And in addition to that, we're injecting PFC tracer, perfluorocarbon tracer, in the frac stages that are going into this middle well here. Now the reason for that is all these other vertical wells here, well, not that one, but that one, those, and this one too, those are in the upper Devonian. Those are 4,000 feet higher than the Marcellus, and they're about midway between the Marcellus and the surface. But these are producing wells. What's nice about that is that should a upward migration from the Marcellus occur, and should it get up to that level, it will be captured in the production of the gas and the water from those upper Devonian wells. So the PFC tracer we're injecting with the frac charges down in the Marcellus, if we see them, in these upper Devonian wells, there can only be one explanation. We have communication between the two zones. Likewise, we're looking at natural tracers too. It'd be strontium. Just as an example here, the strontium isotope ratios for the Marcellus plot in this area right here, whereas those upper Devonian wells plot completely over here. So there's a big difference there. So if any of the water from the Marcellus, which contains high amounts of strontium, get into those upper wells, we'll see it in a shift in this isotope ratio in the produced water from these upper wells. And likewise, we can do the same with the carbon-12, carbon-13 ratio in the methane. They're different. So if that starts shifting in the methane production from the upper Devonian wells, we'll see it there as well. As I said, this hydraulic fracturing is taking place right now. And it'll probably be completed next week. So like in a month, we'll have the microseismic data to know exactly how high these fractures have migrated upwards. The tracers we're talking about here, that monitoring of those will take longer, probably on the order of a year or so, and then we will know. But in this case, well, in addition to the tracers, we also have the aspect that the Marcellus is an overpressured formation, whereas the wells in the upper Devonian is under pressure or at hydrostatic pressure. So if we get a breakthrough between the two zones, we would see a pressure spike in the upper Devonian wells. That would probably be one of the first things we'd see. So we have multiple lines of evidence to determine whether or not there's communication between the two wells.
Thank you, Rick. Our final speaker is Bill Leith, who was recently selected as the Senior Science Advisor for Earthquake and Geologic Hazards at the U.S. Geological Survey. Bill oversees the earthquake hazards, geomagnetism, and global seismographic network programs.
Great, thank you. I'm going to start by just telling you what I'm going to tell you, just in the interest of time. I know that you all are sometimes called away, and I also feel badly for the people who are having to stand. And so hopefully this is the message that if you get nothing else, I hope you get. And the first is that anytime there's an injection of fluid at depth, at the depth at which earthquakes occur, that carries a risk of inducing earthquakes. And that's both injection and withdrawal of fluid, and I'll explain how that happens. Second is that you may have heard hydrofracking causes earthquake in, pick your state, Ohio, Texas, Oklahoma. And in fact, the hydrofracking, the process that Rick just described by itself, it actually rarely triggers earthquakes that are of any significance, and certainly not large enough to be of a safety concern. The third is something that's been in the news lately from a study that USGS did. The rate of earthquakes in the mid-continent has actually increased significantly in recent years. Few injection wells are triggering earthquakes, but this rate increase is in fact associated with the unconventional production that Brenda described to you earlier. And then finally, the risk can be managed. At least that's the optimistic view, and I'll explain the scientific basis for that. Throwing up here a list of earthquakes that have been significant ones that have been induced or that you might have heard about, certainly not all of them. And I do this mainly to illustrate that this is not a new phenomenon. Human-induced earthquakes have been around for more than half a century. And I want to point out a few that I can thread through the rest of the talk. The first is earthquake injection experiments that were done jointly with Chevron in the 1960s and 1970s that provide the basis for understanding how fluid pressure and earthquakes interact at depth. The second is the Rocky Mountain Arsenal, and I point this out because that magnitude 5.3 earthquake is the largest well-documented earthquake that's occurred due to an injection activity. And then there have been earthquakes associated with the filling of water reservoirs with geothermal production, and three that you might have heard of in recent years, the Dallas Airport, in Arkansas, and in Ohio. So again, this is a phenomenon that's been around for a long time and is reasonably well understood. And I forgot to mention, of course, I highlighted here so that you couldn't possibly miss it, the fact that so many of these are related to injection activities. So what types of activities involve injection? Of course, the liquid disposal of all types. And that Rocky Mountain Arsenal induced earthquake, that was from the disposal of nerve gas back in the 1960s. Geothermal production and enhanced geothermals. We have a long-term project working with DOE at the geysers in California, for example, to track the earthquakes associated with the geothermal production there. And then the one we're talking about today, tight shale gas, tight sand, coal bed methane production, the fracking activity, and the earthquakes in this case are associated with the disposal of the produced water. I'll describe that process. And then finally, carbon dioxide sequestration. That's in the pilot stage now in the United States. And it's my understanding that a pilot project in Illinois, there actually are earthquakes triggered there already due to that carbon sequestration. So this a schematic illustrates the process. Then the process that Rick just described is the one down here, the fracking itself. So the well is drilled in the Marcellus, for example, typically turned horizontally, and while 1 million gallons might be injected in a single stage of fracking, and there may be multiple stages of the injection of fluid, schematically illustrated here, as they inject under pressure this large volume of water, cracking the formation, and then pulling back and doing several stages. That produces these micro-earthquakes that Rick described, are monitored sometimes by these downhole arrays, and they're called microseismic monitors because they're micro-earthquakes. These are earthquakes that are most of the time, almost all of the time, less than magnitude 2, and typically less than magnitude 0. They're very small, and they're not the triggering of an earthquake, but they're actually the cracking of the rock itself. What does happen, however, is that during the production phase, in many hydrofraced wells, the gas comes up the well in a large volume of the formation water. This is the so-called produced water, and it can be very large volumes that are produced. And as Rick mentioned, the water is salty, often many times saltier than seawater. So the Clean Water Act says that produced water can't be just dumped in a stream or a lake, and when it's produced in a very large volume, it's not economic to treat the water and then release the clean water. So the associated with the production is, and it's illustrated up here by a truck, that produced water is either piped or hauled away and disposed of in a deep injection well. That's shown in a cartoon here that shows the production well being linked to a disposal well. The disposal wells are regulated by the EPA or delegated to the states for regulation. They're called UIC disposal wells, and there are about 40,000 of them in the United States, roughly. So what happens is that when the fluid is injected deep, and this is typically done deep in order to stay away from the shallow aquifers, when that injection occurs, it has the potential for triggering earthquakes. Why does this happen? So first, we know that below a few kilometers depth, the Earth's crust is everywhere stressed, and we actually know that that the stresses put the rock very close to failure. This is known from stress measurements that have been done across the continent and around the world, and also it's known because, in fact, you can inject water down a hole and you can trigger an earthquake. That means that the rock is close to failure. The second is that the injection, how this works is the injection forces fluid along a fault or a fracture, and that relieves what's called the effective stress. So once you're down deep, the two sides of the fault are pressed together by the weight of the rock above them and by the natural, what we call tectonic stress. When the fluid is injected, when the fluid pressure rises through injection into a fault, that pushes the sides of the fault apart. That relieves the stress on the fault and allows it to slip due to a natural stress. The third, and this is my point from the last slide, the hydrofrac itself actually does not release very much energy compared with the natural tectonic stresses, which are triggered by the fluid injection disposal activity. And then during production activity at many sites of production from these unconventional resources, large volumes of fluid are injected during disposal. That flows along the fault, and that can trigger earthquakes. So how big can an earthquake be that is triggered by an injection activity? And that's shown on this slide, which plots along the horizontal, the area that's affected by the fluid injection and the maximum magnitude. And you see this upward trend here. Those injection-related largest earthquakes are shown with the red squares, and the largest one here, that RMA, that's the Rocky Mountain Arsenal, that magnitude 5.3 earthquake that occurred in the 1960s. So the takeaway from this is for me, quite simple. It means that the larger the area affected, the larger the potential earthquake, and what causes a larger area to be affected? That's more volume. The more volume is injected down a hole, then the data suggests will produce the largest potential earthquake. Now for the situation in the central U.S. A colleague of mine, Bill Ellsworth, and others at USGS in our California office did a study recently which is just very simple. Just count the number of earthquakes. You saw Brenda's animation of the number, the production in the Bakken Formation. That was her hockey stick. This is my hockey stick shown here, and I wish I had it animated now. But so you just start counting from 1970, and we think that at magnitude 3 and larger, we have a complete record of magnitude 3 earthquakes for this region of the central U.S. shown between these two lines. And you see this fairly steady rate. This indicates pretty much of a natural process. It includes quite a number of magnitude 4 and maybe 1 or 2 magnitude 5 earthquakes and their aftershocks. And yet it's a steady rate of about 21 events per year at that magnitude level. Then in 2000, this takes a little turn here and goes up by about 50%. And that turn and that increased rate of earthquakes is actually spatially associated with that dot right here, the Raton Basin in southern Colorado and northern New Mexico. And then in about 2008, you see this take this very sharp trend. It's about 7-fold increase over what it was in the 30 years from 70 to 2000. And those are associated with other areas. You know, Brenda also showed a bubble chart. This is my bubble chart up here. And you see that these are magnitude 4 earthquakes in, for example, Arkansas, Oklahoma, Texas, southern Colorado, West Virginia, and I think, which one did I miss? Oh, and Indiana. So this rate increase is associated with areas where there is production and disposal activities from these unconventional resource exploitation and production. I'm going to give you one illustration, and that's from Arkansas. I'm giving this as an example because it's actually quite well documented now, a collaboration between the USGS and the University of Memphis. So as part of a shale gas play, unconventional fracking and disposal activities, large volumes of water were being injected in the area just north of Little Rock. And the epicenters of earthquakes are shown here as the red and yellow dots, and their time sequence, so that the red dots are the ones which occurred early on in the sequence, and the yellow dots are the ones later on. And the injection wells are those, these are disposal wells labeled number 1, the diamond here, and number 5, the diamond here. Those two wells were injecting, millions of gallons of produced water from the shale gas production operation. So an earthquake of magnitude 4.7 occurred about 15 months ago in this area, and as a result of this may be perfectly obvious, but that defines a fault. So we have an association between the disposal wells and the migration of earthquakes along a fault. What from scientific point of view, helped us out here is that the Arkansas Oil and Gas Commission halted the injection activity at those wells after the magnitude 4.7 earthquake, and the earthquakes rapidly subsided over a period of a couple of months. So here you see a pretty good illustration, well controlled seismologically. We have data on the production and disposal, data on the volumes disposed of on a daily basis from those wells, and then we have the experiment that essentially was done, turning the wells off, having the earthquake subside. This is the same situation that was documented way back in the 1960s at the Rangeley Field in Colorado. The research questions that we're trying to answer are these. First, why did triggered earthquakes occur in some places and not others? Remember, I mentioned there are around 40,000 of these disposal wells, but there are really only a handful of well-documented areas where significant earthquakes have been triggered associated with the disposal activity. Second is, can the injection practices be altered to minimize the risk of triggered earthquakes? And the Arkansas example is one where you'd think, yes, that shows that if you, well, certainly you can turn the well off, but can you also just reduce the volume or reduce the pressure at which the fluid is being injected? Third is the question, the application of that would be, once a significant earthquake occurs, what process changes should be implemented. And I show here the example from Ohio. This is interesting. First of all, it dispels that notion that hydrofracking itself produces earthquakes, because there's no hydrofracking going on here. This is only a disposal well, was only a disposal well, and it's disposing of the produced water from production in Pennsylvania. But you see an epicenter here, which is pretty much in the middle of a suburban neighborhood. And so this gets at the last questions, what about regulation and permitting? Once you've had a significant earthquake, what should be done to try to control the risk of a future and a larger earthquake? There is some optimism for being able to manage this risk. This is an article by Mark Zobak, an expert in induced earthquakes and a professor at Stanford University, published a couple of months ago in Earth Magazine, which describes that. I put this up in case you want to look further at what some of the management ideas are for managing earthquake risk. And then finally, these same key points again. I won't go through them for the interest of time, but again, this is not a new phenomenon. We've known about injection-triggered earthquakes for a long time. The hydrofrac itself is not responsible for the earthquakes that are significant safety-wise. The rate of earthquakes in the U.S. seems to be associated with an increase in the disposal of produced water from these types of operations. And then finally, it looks like the risk can be managed. We have a FAQ, which is frequently asked questions, outside on the table, and that's also online at this website. And our Deputy Secretary of Interior has written about this at the website described below. So thank you very much.
Okay, that ends our briefing. Thank you, everyone, for attending. Thank you, speakers. Thank you very much to Representative Jerry Connolly for hosting. Thanks to USGS. Thanks to AGU for co-hosting. And in my case, the Association of American State Geologists. Thanks to all. If there's further discussion, I think the speakers hopefully can linger a few minutes. Please stay if you have additional questions or discussion. Thanks.